Okay, now we want to set up the variational principle. We discussed the meta Lagrangian, which is generally non-minimally coupled, but seriously we only take the minimal coupling. The other thing is just a trick in order to save some space in the derivation of the neutral identity theta alpha psi a covariant exterior derivative, and then on the torsion and on the branches. Of course, I cannot derive now all details, but I want to show you how this procedure works and how one goes about it. So what you do is first you vary the Lagrangian. And the variation of the Lagrangian, of course, you have to vary your independent pieces, so it's a variation of theta alpha, which partial L over partial theta alpha. You can consider that as an implicit definition of this partial derivative. And then let us first go to the geometrical things. Variation of T alpha, which partial L over partial T alpha, plus variation of R alpha beta, which partial L over partial R alpha beta. These are the geometrical pieces, and then we need the meta pieces. We vary the psi plus variation of psi A, which partial L to partial psi A, and now we have to vary the covariant first derivatives, plus variation, parenthesis, capital P psi A, parenthesis, which partial L over partial covariant exterior derivative of psi A. Okay, this formula is a general formula which let me call it X. I will use it later. Now, the variation and the exterior derivative commute. This is just ordinary variational formalism. And now we have to compute the variation of the T and the variation of R. The variation of T, we just go back to the definition of a T, is D times variation of theta alpha plus D gamma alpha beta, which theta beta. And the corresponding formula for the curvature, the variation of the curvature, R alpha beta is equal, this is a small exercise which we have already, which was already given the last time, is the variation of gamma alpha beta. So these are very compact formulas, and now we substitute this here and the R here and rewrite this whole expression. And we have to, then we find, as a consequence of substituting these two formulas, we find that dl delta L is equal delta theta alpha, which, well, this is now an abbreviation which I will explain in a minute. Calligraphic T alpha, which is the energy momentum tensor, plus variation of gamma alpha beta, which calligraphic S alpha beta, alpha up and beta down, plus variation of psi A, which, and now I introduce a new abbreviation, variational derivative of L with respect to variational derivative of psi A, which I define in a minute, and then I get an exact piece plus these are the pieces which are by partial differentiation, plus exterior derivative of delta theta alpha, which dl over dt alpha plus variation of gamma alpha beta, which dl over the curvature, partial r alpha beta, and finally the deep psi A, which the partial derivative of L with respect to the velocity, so with respect to t partial t psi. Bracket closed. This is a surface term, a divergence, which in the variational process, of course, doesn't play a role, as we know. So this formula I call Y. And I owe you now three definitions. The T alpha, the calligraphic T, the calligraphic S, and this variational derivative. So the calligraphic T, which is, I write it out, the canonical energy momentum freeform is T alpha, calligraphic T alpha, by definition is variational derivative of L with respect to theta alpha. Well, and I have okay, which of course I can write out as this is just an abbreviation for partial L over partial theta alpha minus a plus, because we have here even form d of partial L over dt alpha. T is a torsion. So, so this is just an abbreviation for that. So this is the canonical energy momentum tensor, and the canonical, which we just defined by comparing it with here. We have here a theta, and we pick a piece up from the here. And then we get the canonical spin freeform, which is calligraphic S alpha beta is by definition, and that's analogous. So it's partial variational derivative of L with respect to gamma alpha beta. Oh, here I put the indices, both indices down solid. C alpha beta, S alpha beta is this. And if we express this expression, I won't do it because we don't need it. Well, I should do it. Because this is what you know from canonical field theory as the definition. So you should so this is rho alpha beta, the representation matrices, AB times psi B, and wedge partial DL over E psi A. So this is really the canonical spin, which you know, and then we have this non-minimal part plus theta antisymmetric alpha DL over partial T beta, and we have a corresponding piece for the curvature EL over ER alpha beta. But the leading piece is that these are the non-minimal pieces. If there is no non-minimal coupling, they vanish. So these are. So this is the decisive formula which I really have to frame, because this is identifies these variational derivatives as the canonical tensors we know from classical field theory. These non-minimal pieces are also interesting. And I have introduced here the symbol for the variational derivative, which we already used. So the variational derivative of L over D psi A is equal to partial derivative minus, and then minus the form, P form times EL over E psi A. Okay, so this is these two formulas we use again and again. So usually we are only interested in variations. In the variational calculus, these surface terms only play a role if you discuss the energy momentum or the angular momentum of the insular matter distribution from infinity. Then you integrate over the infinite surface, and these terms are decisive. But for the variational principle, they don't play a role here, only these pieces.
Sorry.
Then we can. Yes.
Should there be a covariant derivative?
Where? There.
Yes.
Okay. Thank you. This is just a definition of the variational derivative, which you know from the Euler-Lagrange relations of classical mechanics. Okay, now we can decompose the. And this is my exercise number 1. Just want to keep people busy. You can decompose the energy momentum 3 form into 3 different pieces. T alpha, and here dagger, and here sort of a smiley, here a circle, a half circle, plus 1/4 times E alpha in theta gamma wedge T gamma plus 1/2 times theta alpha wedge T wedge T. So this is 16, this is the symmetric trace free piece, symmetric trace free. This is the trace here of the energy momentum tensor, which vanishes, for instance, for electromagnetism, and this is the anti-symmetric piece. Anti-symmetric piece. So each canonical energy momentum tensor can be decomposed, and exercise number 1 is proof this relation. In this relation, I have abbreviated T is by definition E alpha in T alpha. This quantity which appears here. This is just the anti-symmetric piece of energy momentum current. And then comes my exercise 2. Which is also manageable, that the canonical energy momentum, the canonical spin S alpha beta can always present it as an exterior product theta alpha wedge a 2 form mu beta anti-symmetric. Prove this formula by explicitly calculating mu. So you just have to resolve this formula with respect to mu, and you find then the proof of this formula. This is used in application quite heavily. So that's exercise 1, and that's exercise 2. And the remark, the usual energy momentum tensors, if you have the energy momentum 3 form, then of course you can decompose it with respect to 3 forms, and so we know the eta with 1 index is a 3 form, so we can decompose it in the following way: T alpha beta times eta beta. Eta is 3 form which we defined at the beginning of the lecture. And this is then the energy momentum tensor. Energy momentum tensor, which is obviously has 2 indices, and the spin 3 form S alpha beta can be decomposed in the same way: S alpha beta gamma times eta gamma. And this is the canonical spin tensor, which you find in textbooks, if they are written in component formalism. And of course, S alpha beta is antisymmetric, so S alpha beta gamma is equal minus S beta alpha gamma. So this is antisymmetric. Okay, now we have all preparations in order to derive the Noether identities. Section 5.3. Noether identities for T and S. Noether identities for T, the energy momentum, T alpha, 3 form, and S, the spin 3 form, S alpha beta. Of course, we have now the variation of the Lagrangian already expressed. We have expressed the variation of the Lagrangian in terms of the currents. And of course, in order to apply, to find the Noether theorems, we have now to investigate translational invariance or diffeomorphism invariance, which is in this context the same, and Lorentz invariance. And then we can derive therefrom, and this of course in curved and torted space-time, contorted space-time, so not in flat space-time, but in in the space-time we are in gravitational theory. So we introduce here for translations a small translation vector, psi, we call this vector. And in order to define the covariance, we take the lead derivative of the Lagrangian with respect to this translation. So what we have to do is the lead derivative, and we take the covariant lead derivative. Covariant lead derivative. L, well, I make this pound sign with a bar in order to, and this covariant lead derivative of an object, of a tensorial object, or it could be also connection with respect to this tensor field. And the covariant one is defined as this vector field in covariant exterior derivative plus d psi in. This is the usual formula for lead derivatives. If you have the partial lead derivative, then here are exterior products. If you have the covariant lead derivative, it's that. And you apply the lead derivative to your Lagrangian, so you sort of carry the Lagrangian along this vector field to a neighboring point, and then you require that this action is zero. This is what is done. So we have the covariant lead derivative of the Lagrangian L with respect to this vector field psi. Okay, and now you have, so this is local translations. Translate a little bit along this vector field. Is okay, now you have to just to apply the variational formula. So you have a lead derivative with respect to psi applied to theta alpha, which dl partial L over partial theta alpha. And the same for torsion. Lead derivative applied to torsion T alpha with respect to the vector field psi, which dl over T alpha, and the same for the curvature plus lead derivative of the curvature alpha beta with respect to the vector field psi, which dl over dr alpha beta. Okay, and now you get the pieces with respect to psi. So we have three pieces: the theta, the torsion, and the curvature. And now we have to have the psi plus the lead derivative of psi a with respect to the vector field, which dl over d psi a, and the derivatives plus lead derivative of exterior covariant derivative of psi a, parenthesis, which dl over d parenthesis d psi e. I think this is fairly clear, hopefully. And of course this has to be zero, because we want invariance under this. And now you have to substitute the definition of the Lie derivative, which we define somewhere here. You substitute it everywhere, and then you use the formulas which we have here and turn the crank after some algebra, which I cannot. It's basically straightforward. If you want to see the details in the physics reports, which I wrote with my colleagues 1995, it's spelled out in detail. You find, I just want to give you an idea how these formulas arise. A plus dB equals 0, the exact term and the A is defined, and these are now the terms which you find. This is also, it's always the same. First with respect to theta, with T and alpha, so A defined minus parenthesis psi in theta alpha, this is the theta alpha term, times covariant derivative, variational derivative of L with respect to variational derivative of theta alpha. And now the same for torsion psi in torsion alpha times variational derivative of L over theta A plus, and now the curvature term psi in R alpha beta also times dl over b gamma alpha beta gamma. I'm sorry, this is the first R is here beta gamma, of course. And the corresponding terms for the psi's, which I don't write out. And for B, you get a similar formula. Psi in L minus bracket parenthesis psi in theta alpha, which partial L over partial theta alpha. And now you get again the terms with respect to torsion. It's all a bit repetitive, but we have to write it down 1 time T alpha, which dl over T alpha plus the term for the curvature psi in R alpha beta times dl over dr